Welcome back, everyone. In this video, we will be covering the third part of Lecture 12. The topic is the fundamental theorem of asset pricing. In the previous video, we learned about a risk-neutral pricing recipe. The recipe told us that the price of a derivative, x0, is equal to its discounted risk-neutral weighted average payoff. That was equal to e to the negative r times t times the quantity qu dot xu plus qd, or 1 minus qu dot xd. Okay, where xu and xd are the payoffs of the derivative x that we are interested in pricing, and qu and 1 minus qu, which is equal to q sub d, are the risk-neutral probabilities. We interpreted this as a discounted, risk-neutral, weighted average payoff, or expected payoff. Okay, the shorthand notation for a risk-neutral expected payoff is e to the q of xt. This is just the expected, what this symbol means is expected payoff of the security x under risk-neutral probabilities. Okay, and when you hear expected, just think weighted average payoffs where the weights are the probabilities. Okay, in particular in the binomial model, this expectation will take many forms depending on what model we're working with, but in the binomial model, we have that this expectation under the risk-neutral measure is qu dot xu plus 1 minus qu dot x sub d. Okay. The risk-neutral expected payoff, again, is just a probability weighted average. It's the expectation, the probabilistic expectation, but where the probabilities are not actually physical likelihoods of things occurring, but they're rather synthetic risk-neutral, or Q, we call them Q probabilities. Okay. Importantly, okay, this result that the price of the derivative was equal to its discounted expected risk-neutral payoff is not specific to the binomial model. It's actually completely general and applies to a whole class of models. It's known, this result, or this main equation right here, is known as the fundamental theorem of asset pricing. What we like to call it is the FTAP for short. The FTAP states that the price of any security is just its discounted expected value under the Q, or risk-neutral measure. Or mathematically, the price of any security x0 is equal to its discounted risk-neutral value or payoff. Okay. The particular model, like we said above, determines how, so this is influenced, model influenced, how this expectation looks. But in general, okay, for even when we get to the Black-Scholes model, the general result in asset pricing is the FTAP, and it says that if you ever want to compute the price of something, all you have to do is take its discounted expected risk-neutral payoff. Okay? The FTAP is actually the single most important result in asset pricing. The reason why it's so important is because it makes almost no assumptions other than no arbitrage. It allows us to price basically any asset using a simple formula. And even more importantly is that the inputs to the formula are all observable in practice. We observe the risk-free rates. We're going to back out the risk-neutral probabilities Q from the asset prices, the U and the Ds, and we're going to know the payoffs as well. So it's going to be very easy to compute actually in practice, which is why it's such an important result. One of the like kind of counterintuitive and important features of the FTAP is that it uses these synthetic, these nonsense risk neutral probabilities, these Q probabilities, instead of what we normally think of as real world or P probabilities. In your other finance classes, you've dealt with P probabilities or real world probabilities. These are the actual likelihoods of events occurring. For example, the actual likelihood of it raining tomorrow. And the key thing to know is that risk neutral probabilities are not physical probabilities or real world probabilities. Q probabilities are not equal to the actual probability of things happening. Okay? Risk neutral probabilities are synthetic probabilities extracted from asset prices. Their purpose is to price assets and generate prices that do not admit arbitrage. They can be, but they're not on a first order basis used to forecast the future. The difference between the risk neutral and the real world probabilities reflects something known as the market price of risk. Essentially, what the risk neutral probabilities are going to do is they're going to risk adjust the real world probabilities P. Risk neutral probabilities are going to be higher in states of the world where the market price of risk is relatively high, and they're going to fall below real world probabilities in states where the market price of risk is low. For example, consider something like a recession. On any given date, the likelihood or real world probability of a recession is low. However, the price of a risk or a price of $1 in a recession or the price of risk in recession is very high. That is, you'd prefer $10,000 in a recession than receiving $10,000 in a booming economy. And the risk neutral probabilities are going to account for this fact that the price of risk is higher in this recession state. The risk neutral probabilities are going to take that real world probability and attach more weight to it for the recession state than its actual likelihood, because it's going to reflect that securities that have good payouts in the state are worth more in some sense. Okay? The key thing to remember though, this is all the economic interpretation. The key thing to remember is that pricing is always done with the risk neutral probabilities. The fundamental theorem of asset pricing, which is what we'll use throughout the entire rest of the class, is dependent on not physical probabilities, okay, actual likelihoods, but risk neutral probabilities that are extracted from asset prices. Okay, pricing with real world probabilities is almost surely wrong unless you make the proper risk adjustment that we'll talk about in the fourth part of these lecture slides. So to make this concept a little more clear, we'll work on a practice problem. I'll give you a minute to read this question. The problem is going to let us actually extract the market price of risk in two states and then make some inferences about why these risk neutral probabilities may differ from the real world ones. So I'll let you read it and then we will solve. Okay. So let's work through the problem. The problem statement is as follows. We have a non-dividend paying stock S. Today's price of the stock is S0 equal to 2. And 1 year from today, there are two possible states in which the stock's price will vary. In the up state, the stock's price is going to be SU equal to 4. And in the D state, the price of the stock is going to be SD equal 1. We're going to be given the real world probabilities of each state. These are the real world or P probabilities, not the Q. The real world probability of the upstate is 1/2, and hence the real world probability of the downstate is 1/2. Continuously compounded risk-free interest rate is 0%. There are 3 questions. First, what are the risk-neutral probabilities? Second, we're given something called a U-arrow security. This security has a payoff of 1 in the U state and 0 in the downstate. We want to price this security using the fundamental theorem of asset pricing and the risk-neutral pricing formula. We then want to price a D-arrow security, which has a payoff of 1 in the D state and 0 in the upstate. And then what we want to do is we want to take the risk-neutral probabilities, compare them to the P probabilities, and then say how does their difference relate to the difference in the pricing between these U-arrow and D-arrow securities. And the big catch is that the U and D-arrow securities are actually what we're going to refer to when we talk about the market price of risk. Okay, so let's start by drawing our binomial tree. We have 2 dates, 0 and capital T, equal to 1 year from today. Okay. Everything is known as of date 0, but in the future at date T reflects uncertainty. Okay. There's 2 states at date T, T equals 1. The probability of the first state, which is U, second state is D. The physical probability of the first state is 1/2. The physical probability of, or the real world probability of the D state is 1 minus 1/2, which is 1/2. Okay. There are 2 basis assets in the model, a stock and a bond. The stock has a price of 2 at date 0. The bond has a price of B0 equal e to the negative r, which is 0 times T1, so it's 1 at date 0. The payoffs to the stock depend on the state of the world. In the upstate, the payoff to the stock is SU equal to 4. This implies that the gross rate of return in the upstate U is equal to 4 over 2, which is 2. And in the downstate, the stock's payoff is S sub D. It's equal to 1, which implies the gross rate of return in the downstate is equal to 1/2. Okay, the bond has constant payoff of B equal to 1 in both states. Okay, and like we said, the real world probability of moving up and down is 1/2. This is the real world, or P probability, not the risk neutral probability. The risk neutral one is what we use to price with. In the first question, what we do is we want to calculate the risk neutral probabilities. The risk neutral probability of the upstate, QU, is equal to e to the RT minus D over U minus D. Plugging in inputs, e to the 0.00 times 1 minus 1/2 over 2 minus 1/2. This is going to be, work it out, 1/3. And Q sub D, the risk neutral probability of the downstate, 1 minus QU, is equal to 1 minus 1/3, which is 2/3. Okay, let's add these to the model. Real world probability of the upstate is 1/2, but the risk neutral probability of that upstate is actually 2/3. Well, whoops, it's 1/3, excuse me. It's less than the real world probability. And in the downstate, the risk neutral probability is 2/3, while the real world probability is 1/2. Risk neutral probability is lower than the real world in the upstate, and vice versa in the downstate. Excuse me. Okay. We now, in the fourth part of the problem, we're going to actually want to ask why this is the case. The thing that's going to give us some insights into why is pricing these U and D arrow securities. Okay. We start by pricing the U arrow security. The U arrow security, we'll write the U arrow, okay, in the upstate is going to have a payoff, or let's write it like this. The price of the U arrow security at date 0 is given by little phi sub U. And this is equal to what we want to figure out. The payoff to the little U arrow security in the upstate will denote it phi sub U of U is equal to 1. And in the downstate, it's phi sub U of D, which is equal to 0. We want to calculate the price of this derivative. Okay. To calculate the price of this derivative, we use the risk neutral pricing formula, or the FTAP. The price of the derivative, phi sub U, is equal to its risk neutral discounted expected payoff. e to the RT, e sub q, e to the q of xt, okay, where this is going to be phi u of t. Plug in our inputs. This is e to the negative 0.00 times 1 times, and we know that this expected payoff in the two-state binomial model and that is going to be given by QU, which is 1/3, times the payoff in the upstate of the U arrow security, which is 1, plus 2/3, which is Q sub D, times the payoff in the downstate, which is 0. This is going to be equal to 1/3. So the price of the U arrow security is going to be equal to 1/3 as of date 0. I just discounted risk neutral expected payoff. In the third part of the question, we're going to want to calculate the price of phi D. Phi D is going to be the D arrow security. It's going to have a payoff of phi sub D of U equal to 0 in the upstate, phi sub D of D equal to 1 in the downstate. They're called arrow securities because the U arrow security pays 1 in the upstate, 0 in the downstate. The D arrow security pays 1 in the downstate, 0 in the upstate. So they're just arrow payoffs. Okay. The price of this security is given by the risk neutral discounted expected value. It's equal to e to the negative 0.00 times 1 times 1/3, which is QU, times 0 plus 2/3 times 1, which is 2/3. Okay. So phi sub D is equal to 2/3. Okay, so we've priced two derivatives right now, or they're actually just securities, the arrow securities in the upstate and the downstate. What we want to do now in this third part, or in this fourth part of the problem, is to use these to compare and contrast the risk neutral and the physical probabilities. Okay, so what we can do is we can draw a little table here. Okay, so we write down the U state and the D state, and we write down Q, which is risk neutral probabilities, and P probabilities here. Okay. Now the P probability of the upstate was 1/2. The P probability of the downstate was 1/2. Okay. And the risk neutral probability of the upstate was 1/3, and the risk neutral probability of the downstate was 2/3. Now the difference between the risk neutral and the difference between the risk neutral and the real world probabilities reflects the market price of risk. Okay, so phi D, which is the D arrow security, reflects the market price of risk in down state. Okay, it's equal to 2/3. It's the cost of receiving $1 in the downstate today. Phi U represents the market price of risk in the upstate. It's equal to 1/3. Okay, and it's the cost of receiving $1 in the upstate of the world. Okay, the risk neutral probabilities, okay, Q probabilities, adjust P probabilities for market price of risk. Okay, the market price of risk is higher in the D state, so the Q probabilities assign more weight to D state than in reality. Okay, so the risk neutral probabilities take the physical probabilities and they perform a risk adjustment to reflect how valuable $1 received in each state is. Both the U and the D states are equally likely in a real world likelihood context. However, receiving a dollar in the D state is clearly much more valuable from today's standpoint because the D arrow security is twice the value of the U arrow security. And the Q probability is going to reflect this fact that it's more valuable to receive payoffs in this down state by adjusting this D probability upwards and this U probability downwards. So that when we perform an expected value calculation, it's correctly taking into account that cash flows in the down state are worth more than cash flows in the up state in a risk neutral sense. Okay, so that wraps up the third part of lecture 12. Okay, we'll take a quick break and we'll summarize in the last video.